We are live.
Okay, thanks. Let me start this introduction in Spanish then. Saludos y agradecimientos desde la Universidad de Guanajuato en colaboración con el programa STEAM de la Universidad de San Carlos de Guatemala. Gracias a todos ustedes hemos llegado a más de 2 millones de participantes desde que iniciamos esta serie de seminarios, en promedio 1,000 participantes por día. Sabemos que nos siguen en este seminario de casi todas las Américas, desde Argentina, Chile, Perú, Colombia, Uruguay, Guatemala, Salvador, México y otros países. También de España, Alemania, Estados Unidos. En este seminario tenemos como invitado a Francis Halzen. Me permito una breve semblanza. Francis Halzen es el Hildate and Gregory Breit, profesor distinguido en la Universidad de Wisconsin, en Madison, y director del Instituto de Física de Partículas Elementales. Halzen es el investigador principal del IceCube, Neutrino Observatory en Amundsen Scott, estación en el Polo Sur en la Antártida, el más grande observatorio de neutrinos desde el 2010. Él imparte esta conferencia titulada IceCube, The First Decade of Neutrino Astronomy. Esperamos que sea de mucho provecho para estudiantes de física y para los estudiantes y público en general. Recibiremos sus preguntas por chat. Francis, gracias por aceptar impartir este seminario para muchos estudiantes y público en general del mundo. Now let me say some words in English. Thanks, Francis, for accepting speaking this seminar about IceCube, the first decade of neutrino astronomy. You are very welcome. Thanks, and the public is yours.
Thank you for this kind introduction, which I understood, by the way. I learned Latin and French, so I can handle Spanish a little bit. This will be a slide. This will not be an official IceCube lecture. I will, in this talk, trying to speculate on what the sources of the cosmic rays are. I should say ahead of time that this is a bit of a speculation. We don't have solid data to prove it, but we will eventually, or we will find something different. But before I talk to you about discovering cosmic ray sources, I'm going to give a brief introduction why we are doing neutrino astronomy and what IceCube is. So, you know, I'm not an astronomer, but it's easy to understand how particle physicists like me enter into this subject. Astronomers have been incredibly successful at looking at the sky in different wavelengths of light. And for instance, you are looking now at a slide that shows the Crab Nebula. It's a supernova, a star that exploded in 1052. And you look at it in different colors. For instance, here you see it in radio waves, in infrared, invisible light on the top right, ultraviolet, X-rays, and gamma rays. And you see in X-rays, we suddenly saw jets of particles coming out of the core of this object. So the idea is that you look at different wavelengths of light, you always see different objects in a different way, and you discover objects which you may not have seen before. The problem with this is that it's gay immense. At very large wavelengths, we can look at the sky in gravitational waves. At very short wavelengths, the sky turns dark. And that's where neutrinos come in. So if you try to go to smaller wavelengths than gamma rays, or higher energy particles, then the sky turns dark, and that you can see actually from the data I will show in a minute. But the idea is that instead of doing astronomy with just light and gamma rays, you extend astronomy from multi-wavelength to multi-messenger astronomy. And on the one end of the spectrum, you do it with gravitational waves, on the other end of the spectrum with neutrinos. So here is kind of the same picture, but now you are looking again at you are looking, instead of at one object like the crab, we are looking at a whole universe as a function of the wavelength of light. And so this is the amount of light that's in the universe, spread throughout the universe, as a function of the color. You see here, thermal photons, CMB photons, they dominate the sky. These are the 411 per cubic centimeter. And but the sky is filled with light from all kind of wavelengths. This is the radio sky. This is the sky in infrared light, in visible light, in X-rays, and in gamma rays. And this is what I was talking about. At some point, this game ends, and the gamma ray sky just turns dark. Why is this? Suppose we are looking at an object that emits gamma rays very far away, like some galaxy. These gamma rays don't make it to our detector on Earth, because as I said, the sky is filled, for instance, with microwave photons, and this gamma ray will run into a microwave photon and make an E plus E minus pair. And once you produce charged particles, you have a problem, because the reason we actually don't know, for instance, the origin of cosmic rays is because cosmic rays are mostly protons, they're charged particles. And so we detect them at the Earth, but they move through the magnetic field of our galaxy, of the universe, but then eventually through the magnetic field of our galaxy, and they get bent by the magnetic fields. And so they don't tell us where they come from, like this proton, which I've exaggerated a little bit. But the idea is that charged particles reach the Earth in totally diffuse form. They don't tell us what their sources are. And so cosmic rays were discovered in 1912 by Hess. And here we are more than a century later, and we haven't solved this problem. So the idea is to solve this problem with neutrinos. By the way, this gamma ray will not stop there. This a plus and minus pair will radiate and make an electromagnetic shower. And I'll come back to this concept later. But for now, the ideal way to solve this problem is to do astronomy with neutrinos. Neutrinos are exactly like photons, except they don't interact. Essentially don't interact, which is an advantage because it means we collect photons from the beginning of time and from the edge of the universe without being attenuated, without being absorbed, without being bent. The problem is that they are also difficult to detect. And that's the problem we had to solve. You know, nobody ever told me doing neutrino astronomy is uninteresting. The question was whether it was possible at all. And so is this problem interesting? Well, let me go back. So the idea is to look at this dark universe, which we actually have never seen. And we know that cosmic rays are produced there. So this is a universe that's dominated by charged particles, and they are produced in some sources and accelerated. And so I got interested in this problem. I was always interested in cosmic ray physics when some modest experiment in Utah called the Fly's Eye detected a 300 million TeV cosmic ray. So you have to convert, this is 100 million times the energy of the particle beams at the Large Hadron Collider at CERN. So if you would accelerate this particle with a collider you would have to fill the orbit of Mercury with LHC magnets. And I think it's safe that that's not how nature does this. So we are going to try to solve this problem with neutrinos. So a little bit about the physics first. This is the cosmic ray spectrum, which most of you have seen before, and the details don't matter. At the lowest energy, cosmic rays are actually accelerated in the sun. We know the source and we know how they are accelerated. I am interested in the cosmic rays, the very highest energy cosmic rays, like the one I just talked about. And not only are these energies of the particles very large, but the luminosity of these cosmic accelerators is enormous. And so you have to find sources that not only accelerate to high energy, but do it with high luminosity. And this is very difficult. However, you know, theorists are never short of imagination. And here is, I'm not going to go through this slide. I just want to tell you that given that we had 100 years to think about it, there were a lot of ideas of how you accelerate particles like this. But, you know, no consensus. So the only way out is to try to solve the problem. And I'm going to tell you now how neutrinos are the way to do this. In fact, I'll give you one, and you will see later why I chose this example, right? I give you one example of a cosmic accelerator. Given the large luminosities, every idea somehow involves a black hole or a neutron star or some collapsed object which of which you can tap the gravitational energy. So for instance, particles falling into a supermassive black hole, like our own galaxy has a supermassive black hole, 6 million solar masses. Particles falling into it can be accelerated by the gravitational energy released by these objects. And so this is happening in a place close to the black hole where there's a large amount of radiation. And so what you need, so this provides you with an accelerator, the black hole, and a target to produce neutrinos, because the light surrounding the black hole can act as a target. And the physics is well known, 1950s, a proton and a gamma ray make a neutron and a pi plus, or a proton and a pi zero. And then the pion decay into a muon neutrino and a muon, and the muon decays into a positron and 2 more neutrinos. The pi zero decays into 2 gamma rays. So if you add this up, you get a muon neutrino and an anti-muon neutrino for 2 gamma rays. So the important concept that will return in this talk, and that's where the multi-particle astronomy comes in, is that the multi-messenger astronomy comes in, is that for every neutrino you see in this talk, there is a gamma ray. And that will be very helpful at deciphering the physics. So this is the NASA propaganda picture, a central black hole surrounded by radiation. Somehow particles fall in, are accelerated, and an accelerated proton can meet a gamma ray and produces pions that decay the way I just described. Now, there is something very interesting about this, is that you need protons to make neutrinos because they are the decay products of pions and also kaons. charm particles. But you need protons. You cannot do this with electron beams. And so protons mean cosmic rays. So any source you detect in neutrinos will be a cosmic ray source. So we cannot be confused. Whereas if you look, we see very high energy gamma ray sources, but they are mostly produced by electrons that are accelerated everywhere in the universe and radiate light. We can never make sure that we are looking at a proton source. With neutrinos, it's unambiguous. So then the next question is, how big a neutrino detector do I have to build? And the first answer to this question came from Zatsepin and Berezinski in 1969. And so they speculated about this. You understand this figure now. This is the gamma rays flux in the universe. This is the cosmic ray flux at the time. And you see, these are the cosmic rays we are talking about. These cosmic rays fill the same universe as all these gamma rays. So what will happen is that a cosmic ray will meet a CMB photon and make a neutron and a pi plus, and the pi plus will decay into a neutrino. And so they calculated that you need a neutrino detector of 1 kilometer cube to see these so-called GZK neutrinos. That's what we call them now. And the problem is, since 1969, theorists have been calculating through all the models and the possibilities that I showed on that earlier slide. And somehow this 1 kilometer cube idea came back in many disguises. And so we had to admit to ourselves that it takes a kilometer cube detector to do this type of science. So how do you build a kilometer cube detector? Well, we know how to build neutrino detectors, and rather big ones. This is the Super K detector in a mine in the Japanese Alps, Super Kamiokande. And so you need water and photomultipliers. But this detector is 10,000 times too small to do neutrino astronomy, according to the best of our guesses. And so the way to solve this problem was known for a while. So what was suggested was by Markov in 1960 is that you go deep in a lake or an ocean and fill a kilometer cube of water with photomultiplier tubes. It's very much like the picture I showed before, the Super K experiment. Then you look for neutrinos coming up to the Earth, because when you see a particle coming through the Earth, it can only be a neutrino, nothing else does. And so what it will do is, as they don't interact, they go straight through your detector. But at the energies I will be working, TeV, 2000 TeV, they occasionally hit a nucleus in oxygen or hydrogen and make secondary particles. This is what theorists call deep inelastic scattering. And so if this is a muon neutrino, it will make a muon. And the beauty of the muon is that it has a range of kilometers at this energy. So even if this happens outside your detector, it will stream through your detector and you can detect it. And this muon, because it's charged, unlike the neutrino, will emit light. And as these high energy muons going close to the speed of light, but the speed of light in water is 3/4 of the speed of light, you get a shock wave of light, just like, this duck creates a shock wave because it moves faster than the speed of the waves on the water. And so you use your photomultipliers to map the shock wave. That tells you the energy, the direction of the muon, and it tells you the direction of the neutrino, because at high energy they are aligned. All the physics in this is well understood. It's standard model physics. So this was attempted by a group in Hawaii called the Dumont experiment, and they were pioneers, but they didn't manage to build a detector. And so in the late 80s at Wisconsin, we made a proposal to try to build a detector not in water, but in ice. And so what you have to find is an optically clear medium shielded from cosmic rays. You have to understand its optical properties. You have to fill it with photomultipliers, and you space your photomultipliers about the absorption length of the blue light that this muon emits. And so the largest the absorption length, the easier it is to fill a kilometer cube with sensors. Then you add data acquisition and computers. And we actually established, it took almost a decade, that ice 1.4 kilometers below the geographic South Pole was actually an adequate medium to do this, to implement this proposal, which Markov made at the first Rochester conference in 1960. Since then, it was just a matter of technology. So in comes IceCube. So in fact, in 1988, at the first Venice meeting, I have a talk where I mentioned in summary, this is a detector that requires a number of happy accidents to make it feasible. But if these should come to pass, it may provide at least the least expensive road to a truly large neutrino telescope. And so we started studies at the South Pole. We were lucky in many ways. And the two ways we were really lucky was that the National Science Foundation had a station that could support this experiment. So this is the geographic South Pole where my pointer is now. And you see behind it the National Science Foundation station. This is the IceCube project, and this is the runway where the planes go in and out of the South Pole. And we actually discovered that this ice becomes bubble-free below 1.35 kilometers. And the absorption length of blue light is varies between 100 and 250 meters. In fact, approaching 300 meters in certain places. So this was a wonderful discovery. In fact, the ice below the South Pole, at the time we discovered this, you couldn't make such a substance in the lab that was that transparent. And of course, it's just a consequence. This is 60,000-year-old snow compacted, and it's ultra pure. And that gives you this large absorption length. Here you can see a picture of the detector. Of course, you cannot go down in the ice, but ground-penetrating radar. A plane flies over the South Pole and bounces radar from the bedrock. This is the South Pole surface, which I indicate now. This is the bedrock. So here, this is the solid ground, the solid rock under Antarctica. And so you go 1,450 meters deep, and there you find the IceCube detector. And you can find here, you can see, this is Amanda, which was the smaller R&D prototype we built earlier and is still there. And so even at the bottom of the detector, there's still about 450 meters or more to the bedrock. So we were in the right place to build this detector. So the easiest part is to get photomultipliers. You buy them commercially. And so you put them in a pressure vessel, and then you add electronics, which will digitize the light that the photomultiplier collects. And so if you could go down in the ice, this is an artist's concept, you would see these strings a kilometer long with a 10-inch photomultiplier every 17 meters. And if you go 125 meters away, there is another string of 60 photomultipliers. And 86 of these strings fill a kilometer cube volume. And so I'm first going to tell you how you deploy, because there was another gamble in this. The gamble was not just the optics of the eyes. The gamble was whether we could actually deploy these photomultipliers at this depth. The technique we used was used on a very small scale, drilling into glaciers. But we had to scale this up over a depth of 2.5 kilometers and a width of a hole of 50 meters that could contain these basketball-sized photomultipliers. So the top 80, 90 meters at the South Pole is snow, which you just melt. But then you get solid ice. And so this is the hot water drilling technique. You have a nozzle that falls by gravity and just melts the ice. And it melts the ice over the right width. And after 2.5 days, 2.5 days, it's at depth. This requires a 4.8 megawatt heating plant. So this nozzle delivers 200 gallons per minute of boiling water under pressure. And so 2 days per hole of 2.5 kilometer depth. So you drill actually 3.5 centimeters every second. And so what does this look like? Well, this is the drill tower, which is being set up. So it's a system on sleds. And it's like a circus train, right? And here you see, for instance, here you see a 2.5 kilometer hose that will bring down the hot water. And the 5 megawatt heating plant is basically 40 car wash heaters driven by generators and normal fuel. And you see after the 2 days, the drill comes out of the hole. Ice is an insulator. So the liquid water stays in its liquid state for a day or more, typically. And during that time, before it refreezes, you have all your photomultipliers ready, and you actually make the detector in real time while you are lowering the string. So this is the cable that brings down the voltage to the photomultipliers, and it brings back the digitized signals of the light that they detect. So you see, that's the last time you see your photomultiplier. It goes to depth and it's frozen in forever. So in this picture, you see during the month of December and January, you see 20 cables coming from 20 holes that go into this building, 2-story building at the surface. And this building contains the computers that collect all these signals. There is actually no IceCube detector. There are these 5,000 plus photomultipliers that whenever they collect light, they send the digitized information to the surface, and then computer at the surface combine this information in neutrino events. So what do you see when you turn on this experiment? Well, unfortunately, you see background. Cosmic rays interact with our atmosphere, and just like in the cosmic accelerator, they produce pions that decay, all the same physics. So the atmosphere glows in neutrinos and muons. that reach this detector, even though it's more than 1.5 kilometers deep. So this is what you see. You know, just large number of muons. This is a muon bundle that just came through. And so you see the computers continuously reconstruct muons. So per year, this movie actually repeats, as you can see, it's 10 milliseconds long. Per year, we trigger 100 billion muons, 100,000 neutrinos produced in the atmosphere, 1 every 5 minutes. But and in 1 year, we also managed to detect 200 neutrinos coming from beyond the atmosphere, from the cosmos. And I'll explain next how we do that. So the best way to explain this is to show you an event. So these dots, these colored dots, well, these are the strings, the 86 strings. You see there, the dots on the strings are the photomultiplier. And if light is detected, the dot gets colored. This is our online display. This is 1 photon. The bigger dots may be 100 photons. And the red to green, you follow the rainbow, gives you the direction of the light going through the detector. So here is the movie. The muon comes in from the right, you see, and it streams to the detector. You can tell its direction by eye, but the computers actually can identify the Cherenkov cone and the light emitted later in the process. And so, explanation, a muon coming through the Earth. This comes about 10 degrees below the horizon, comes up through the Earth, produced by a neutrino, by deep inelastic scattering. And the interesting thing about this event is that you measure the energy in the detector, and it's 2,600 TeV. That's too high an energy to be produced in the atmosphere. In fact, this single event is almost a 5 sigma discovery of a cosmic neutrino. But we're going to do better than that. Here you see the data taken after 9.5 years. We actually made this discovery after 2 years, but I'm going to show you the better data. So the threshold of this detector, so this is the number of muons as a function of their energy. You can just think of this as neutrino energy. And so the threshold of the detector is about 100 GeV here. Then you rise over threshold. Most of the muons, atmospheric muons, we detect are about 1 TeV. And then we go to higher energy. And the flux of atmospheric neutrinos falls. This has been measured by many experiments. We understand this flux. We can calculate it. We can measure it. And so at some point around 100 TeV, we see more muons than expected. These come from the cosmos. So the blue line is the extrapolation of the atmospheric neutrino flux. And this excess is the cosmic flux. So we fit this curve as an atmospheric and a cosmic contribution, and then you can calculate the flux. The flux we show is E square. The flux is the number of particles as a function of energy, the NDE, but we will usually plot the energy rather than the number of particles. So these boxes are 2 measurements of the muon cosmic flux. The width includes the statistics and systematics. So this is a many sigma discovery, well above 5 sigma. each measurement we took. But you see here, there is another measurement. These are electron and tau neutrinos. And so how do we detect electron and tau neutrinos? That's actually easier to explain. A muon neutrino interacts with a nucleus and makes a muon, but an electron neutrino will make an electron, and an electron will make a shower, an electromagnetic shower in the ice, which at these energies is about 7 meters long. But a 7-meter long shower of particles emitting Cherenkov light, emitting light, is a point source of light in a big detector. So you see, this is an electron neutrino. It's a ball of light. It's like someone turns on a light bulb in your detector. And I show this here. You can see on the left, on the right is the event I just showed. On the left, you can see an electron neutrino. In fact, we now know you are looking at a tau neutrino in this particular event. And so, you know, it's a calorimeter. You can measure the energy very well. But measure the direction of the source shower is much more difficult than measuring the direction of this long muon track on the right, which we can now do in typical events, high energy events, to better than 0.3 degrees, which is not bad, and you will see good enough. Okay, so to make a long story short, this is our best muon measurement at this time. This is our best electron tau measurement. The green is the background from cosmic rays, from atmospheric neutrinos. And of course, these atmospheric neutrinos, we also do interesting physics with, but you see, we actually begin to see a turnover in the flux. And this could very well be the threshold for P gamma producing the delta resonance decaying to neutron and pi plus. So the delta resonance seen by Fermi years ago, the 1950s at Chicago, we are now seeing in the sky. This is not proven yet. This is what I'm working on at the moment, and I don't have the definite answer proof yet. But I suspect it's right. Anyway, I'll come back to that. So you saw that the electron, tau, and muons kind of fall on top of each other. And so that's, we can measure the relative number of each. And so this is the IceCube flavor triangle, where here at the top is a source that only emits muons. When you propagate, it's you oscillate the muons from the source far away to your detector, you end up here. This is a source only emitting electrons. Sorry. You end up from here, you end up here. This source is when you produce a delta resonance and where you have, like in the atmosphere, 2 nu mu's for every nu e, and then you end up here. So simply, if you produce pions on the in the sky and you propagate them over large distances, they come in equal flavors. In fact, the quantum packages of each flavor have already separated. They don't really oscillate anymore. And so this is exactly the answer we find. It's a bit disappointing. This is the standard model answer with 3 neutrinos. So if we end up anywhere else in this triangle, we discover new physics. But at the moment, we don't. And we are actually at the moment deploying a detector at the South Pole that will help us doing this measurement much better by deploying 7 additional strings, which at the moment 6 have been deployed. So you say, well, this all looks interesting, but do we learn anything? And we didn't realize it for a long time, and that's where my talk becomes more personal than a review. There are two surprises in this data which we didn't recognize at first. The first is that in this universe, dark universe, the neutrino flux is actually larger than the gamma ray flux. You know, neutrino physics is supposed to be something exotic. And the other surprise is that we didn't see the Milky Way. So let me come to the easy one first. Here you see the Milky Way as you see it when you go out at night in the right place on Earth. And you see this is a map of the universe in galactic coordinates. And the major ellipse is our own Milky Way, is our own galaxy. And it's easy to show by simple geometry that the light reaching us from our own galaxy should dominate the light coming from all the other galaxies combined. Just geometry. We should see our own galaxy first. And that's true in every wavelength of light. So this is the sky in gamma rays. So you see your own galaxy, and then you see these points out there. This is a subdominant contribution to your map from other galaxies. Well, here is a map, an old map actually, only 200 events. We have 1,000 now or more. Of cosmic neutrinos, and you see this map is totally uniform. There is no galactic plane. It's in the same coordinates as these. So it means that there are sources in other galaxies that are making neutrinos that don't exist in our own, because if it existed in our own, we should see the Milky Way in neutrinos. Okay. So remember gamma rays from neutral pions producing E plus E minus pairs. Well, simple electrodynamics allows us to calculate what happens to these electron-positron pairs, and eventually they come out as many gamma rays at 10 GeV by the time this shower reached the Earth. And we have a satellite, actually, the Fermi satellite, which can detect this gamma rays. And you see, here you see again this, look at there, you can see again the sky turning dark. Of course, this is due to the presence of CMB, infrared photons filling the universe. So we can go the other way and we can calculate what actually the flux is before it gets absorbed. And you see the neutrino flux is higher. Nobody expected that. And for every neutrino, there is a gamma ray. So where are these gamma rays? Fermi doesn't see them. In fact, we know that Fermi sees objects called blazars, which probably don't produce neutrinos. In fact, we have shown we don't see the sources Fermi sees. So the answer is actually simple. There's no mistake there. Here is another picture of this. This is the extrapolated flux. Here is the neutrino flux. This is the proton flux, by the way, the cosmic ray flux. What happens is what happens at Fermilab. At Fermilab, neutrino beam is not accompanied by gamma rays. If you have a good target that produces a lot of neutrinos, it will absorb the gamma rays from the pi zeros. And these gamma rays appear at lower energy. In fact, they appear, we don't know, we guess they appear clearly below Fermi threshold somehow, maybe at MeV energy or below. So that was the first surprise. And by the way, this is the calculation. The optical depth of a target to gamma rays is 1,000 times larger than the optical depth to protons for producing neutrinos. So the ratio of the cross sections is 10 to the 4, but there are some kinematic factors. So there's no way when you produce neutrinos in a target that the gamma rays can come out without being absorbed. So then we finally, after 10 years of data, we discover the source in our own data. And here it is. It's an active galaxy, NGC 1068. What's an active galaxy? It's a galaxy like our galaxy, but it's active. Active means that it's absorbing all the matter it's cannibalizing. It's also all the hydrogen and electrons and radiation fields are absorbed. Whole stars are absorbed in this black hole in a swirl of matter that's called the accretion disk. And that is a place I already mentioned before. It's the example I gave. You have matter falling into a black hole. If it taps a small fraction of the gravitational energy and transforms into acceleration, you get protons accelerated everywhere in this region. In this region, which glows in light. So there is a large there are large targets for producing photons. So it's for producing neutrinos. It's exactly the type of system we, some people anticipated. And in fact, the surprise of this we found is that the neutrinos actually originate within 10 Schwarzschild radii of the black hole. And that was another surprise. So here is 1 year of data, 138,000 neutrinos. And if I take a small section of this 4 by 4 degrees or so, you can see here, this is a source. It's not particularly the source I just showed, but you see the red dot shows a source. I've forgotten which one it is. And but if you don't color the dots, you don't see the source, right? So how do we find it? Well, we step through the map, point by point, and ask the question whether there are more neutrinos in that point than in the uniform background produced by atmospheric neutrinos, and whether these neutrinos have on average higher energy. So you look stepping through the map for a place with more neutrinos with higher energy. And there is a mathematical way of doing this. It has the advantage that you can count your trials and actually give a real significance to your detection. And so when we did this with 10 years of data, we found this source. You cannot see it, but it's red. It's 5.3 sigma. And it's centered close to this nearby active galaxy. So we have also a method where we look at 110 pre-selected sources, again, totally blind analysis. We find the same source. And so the source, even after we include the trials, is 4.2 sigma, but that's a p-value. So that means that the chance that this is an accident is less than 10 to the minus 5 or so. So this is a definite detection. So you can see here, this is the standard way. This is a map of the p-value of the test statistic. You see here the astronomical source, and that's where we reconstruct it. And you see this is a plot of the neutrinos away from the source is, of course, the peaks in the direction of the source. And you see this signal of 100 neutrinos over the uniform background. 3 years later, we did this again, and now we find 180 neutrinos here. We find 100 neutrinos, and the spot moves closer to the source. In fact, this is most impressive. When we detected it, I just showed, was 0.35 degrees away. Now we did an improved analysis, and it moved to within 0.11 degrees. And then we added data, and it's now within 0.04 degrees of the real astronomical position. So this picture just repeats what I already said. You know, lots of ways to accelerate particles close to the black hole. In fact, the favorite model is that turbulent magnetic field on the infall, on the accretion disk, is what accelerates the particles. But the other thing is there's a huge light-emitting plasma close to the black hole, and it emits large amount of X-rays. That's what astronomers call the corona. So we think that our flux is produced by accelerated protons interacting with X-rays. Here is the data. Here are two theoretical models fitting this, and here you see the absence of gamma rays. A gamma ray experiment in the right energy range, in fact, in some places, shows that the gamma ray flux is suppressed by a factor of 100. So now I can do a theoretical calculation, which I won't do. I will just describe, you can look at the 2 slides later. But I'm going to tell you in words. Okay, so you have protons accelerated living into this corona of X-rays. So by P gamma interactions, you produce neutrinos. So how many neutrinos do you produce? This depends on the optical depth for P gamma interactions, which is the P gamma cross-section times the number of gamma rays in your target and the radius of the target. This can be explained in words, right? The gamma rays, the number of gamma rays is not negotiable, neither is the cross-section. It's given by the luminosity. The astronomers tell us what the number of gamma rays are. The only thing we don't know is what the radius of the target is. And so then, of course, if you make the radius smaller, you get the same number of photons in a smaller volume, you get more pions. And it's more difficult for the gamma rays to get out. And so you ask the question, what's the radius where you produce 100 neutrinos in 10 years and you absorb the pions by the gamma rays by 2 orders of magnitude? And the answer is that the radius is 10 Schwarzschild radii. By the way, that's a distance that's very hard to reach by any telescope except the strongest radio telescopes. And so here is the calculation. In fact, the 2 slides do the calculation for you. So here you can see how the flux, this is another neutrino. And you see how, just look at the top, at the moment the neutrino is emitted, how the gamma ray flux disappears because the target that produces the neutrino at that point absorbs the gamma rays. There are several other examples like this. And you noticed also from the formula that this predicts that the number of neutrinos, which is proportional to the optical depth, is proportional to the X-ray flux, the X-rays in the corona. And so if you plot the neutrino flux versus the X-ray flux, you see the sources we know, we think, we observe lining up. We used this and turned it around and looked for sources with high X-ray fluxes to see if they were neutrino emitters. And we immediately discovered a new source, NGC 4151. And these were also the two brightest sources that Seifert detected with an optical telescope in 1943. So the best fit to the map after 10 years is to fit with three sources: NGC 1068, TXS 0506, and this PKS source. In fact, the happy surprise was this TXS force we had already discovered in 2017. I'm not going to go through that, but in a multi-messenger campaign, we discovered this source tracking a neutrino of 300 eV energy, and later we discovered this source in our own data. This picture now, when you specify that you want X-ray sources, has become this. So we have now 12 sources in the sky to fit our data. So the sky has become very non-uniform. And many of these sources we have seen in different ways, like I won't explain what alerts are. And in fact, some of these sources have even been seen by the Antares telescope, which is much smaller, but gets a hint of some of these sources. So we can somehow start to guess what the sources are. And so let me conclude by telling you that we actually did see the galaxy eventually. And when I told you that the diffuse flux tells us that the gamma ray, the typical source in the diffuse flux should not emit gamma rays, we should have immediately thought that the reason is, what's the source that makes neutrinos in other galaxies? We know the answer now: active black holes. We don't have an active black hole. And so, but we did discover the galactic flux. It's made by cosmic rays interacting with material in our own galaxy. And so you see here our galactic plane superimposed on the sky. But here we can show this is the galactic plane in many wavelengths of light, and here is the galactic plane in neutrinos. And you see it looks similar to other wavelengths, except it's only there where it dominates the sky at all these wavelengths. In neutrinos, it's there at the subdominant level. And so if indeed the cosmic rays are made by these active galaxies that we have identified in a reasonable number now, then the dominant way of producing neutrinos with an active black hole is not present in our own galaxy, and explains its absence. So I'm going to stop here. Here are my conclusions. The important conclusion is that neutrino astronomy exists. There was actually no guarantee that a kilometer cube detector would be sufficient to do this science. In fact, it wasn't until we went through a lot of improvements with the detector after we made some early discovery after 2 years. But to do the physics I described to you, we had to make great improvement in calibration and data analysis. And of course, the galactic plane was only discovered because of machine learning. There's no way with standard techniques of particle physics to extract that galactic plane from our data. I don't think I didn't try to convince you that we have solved the cosmic ray problem, but I think we have a method to solve it. Maybe there are other sources and we'll discover them later. That would actually be exciting. But remember, there is a cosmic ray problem that has not been solved. And that's what are the sources of galactic cosmic rays? And however, now we have neutrinos from our own galaxy, and we'll do our best to try to help solve that problem. But I have the feeling it's going to be much harder. This is the future, and lots of telescopes. This is becoming a real astronomy. Larger telescopes, and many of them already under construction and taking data. And Baikal telescope and KM3 have already found confirmation of the fluxes we saw with IceCube. And so this is becoming real astronomy with a bright future. Thank you very much.
We thank you, Professor Halzen, and on behalf of Dr. Julián Félix, director of the International Elementary Particle Laboratory at Universidad de Guanajuato, and myself, coordinator of the STEAM program, we wish to thank you and again congratulate you on the APS Medal. I know it's one of many honors you hold, but it was an exciting talk, and we have many questions. At this time, we have reached over 600 views on our different channels. And we have a special surprise for you. One of our views is from one of our guests, which is David Lopez, a 10-year-old who is running a cosmic endeavor that is the Quetzal Astronomy Club. He's a 10-year-old that has won several awards, amongst them one being a promise for the youths, and he's going to pass you a question. But before that, we have a couple of questions from the audience, mostly the technical ordeal. One of our viewers asked how difficult it is to fix a PMT or to change or exchange it after it has been set on ice.
It's impossible.
Is there a way?
No,
Oh,
it's impossible. If a PMT dies, it's gone. However, this is, I didn't emphasize this. You know, you deploy these strings, and refreezing is a very violent process because the water is colder at the top than at the bottom. So it freezes in from the top, this column of water. And so you get a
seems Professor Halzen has some tech issues. He is going to be right back. Pero queremos darle la bienvenida a David López y Pamela López, quienes nos acompañan desde el NOC-IAU y desde Constelación Quetzal. Que no sé si tienes algunas palabras para comentarnos en lo que el doctor Halzen regresa.
Hola, muchas gracias por la invitación. Y aquí tengo una pregunta curiosa para el doctor Halzen.
Perfecto, dale un minuto a que logremos reconectarlo y en lo que logramos reconectar al doctor Halzen con un pequeño problema técnico que tenemos, cuéntanos un poco de Constelación Quetzal. Hemos visto que ha crecido mucho y te felicitamos. Cuéntanos.
Bueno, Constelación Quetzal nació como una iniciativa para que los niños puedan aprender más, porque cuando yo quise aprender no había muchos lugares de donde pueda ir, entonces la idea era apoyar a más niños que no tuvieran esa dificultad y que pudieran llegar a cumplir su sueño.
Excelente. Bueno, deseamos que tengas suerte y cualquier cosa, pues desde el programa STEAM y desde los seminarios Leon Lederman estamos para apoyarte. También entendemos que mucho de este esfuerzo Está apoyado por Pamela López, la ingeniera, entonces le mandamos un fuerte y cordial saludo. Y el doctor Halzen ha estado con nosotros el día de hoy promoviendo los últimos avances de 10 años de astronomía de IceCube. Y lamentablemente hemos tenido un problema técnico que esperamos se resuelva rápidamente. Ya tenemos de vuelta al doctor Halzen. Welcome back, Dr. Halzen. You're mute.
Can you hear me again?
Yes, perfect.
Okay. All right.
All right. Great. And now David has one question that he's going to be doing live with you.
Okay.
David, if you want to introduce yourself to Dr. Halzen and ask your question.
Hello, I am David. I am 10 years old and I live in Guatemala. And thanks for the information, Dr. Hansen. And the question is, if you could discover just one more thing about the universe using neutrinos, what would you like to know and why?
Oh, that's a great question. And it's easy to answer. What you want is a complete surprise. Something that, nobody ever thought of. And in fact, we may already have had such a surprise. During its construction, the neutrino telescope that's being built in the Mediterranean Sea saw an event of 220,000 TeV. An IceCube in its 13 years has never seen such a thing. So it's too early to speculate, but there may be things going on in the neutrino sky that just totally baffle us, this is complete surprise. We really cannot explain this event. And that's what you want to see happen, right? As long as you confirm what you anticipate, that you are not learning new things, right? You want to learn things, you want to see things you don't understand. And that's, I'm hoping, and I'm hoping for that, and we already have a hint from this enormous event seen by our friends in the Mediterranean. Does this answer your question?
Yes, thank you.
Thank you.
Great. And one last question from our viewers is, this is the first time that I have seen a map or the flux of the neutrinos, like the microwave cosmic background. Is this data showing us that we have 12 possible sources of neutrinos in the universe? And does this open a new path to the dark matter astronomy?
That are two good questions. So the way you have to look at this map, right? When you fit the map with sources, we find 3 sources after 10 years. We find 12 sources after 13 years. Actually, I think it's more like 15 years now. And so as you accumulate more and more data, this map will contain more and more sources, and it will be clearer what the physics of the cosmic ray sources is. So it's just a matter of how many sources, what actually the sources are, and how many we need to figure it all out. The future will tell. And one way is to take more and more data. There is, however, another way, that is to build a bigger detector. And then you will see many more sources instantly. And that's what we are trying to do. I have the slide still in front of me. You see, we are trying to build a detector. We have proposed to build a detector. We have designed it 10 times bigger. And there are proposals in China to build a detector that's 30 times bigger than IceCube. So, yeah, there's no magic in the 12 sources. It's just as far as we can get with our present data and the precision of our present data.
Oh, great. That certainly is an interesting time to be doing physics.
Yeah, exactly. And it's exciting. You know, for 10 years, we had no competition. And you would think that's great. Actually, it isn't. Neutrino astronomy was a very lonely place because, you know, everything you found, it couldn't be checked by other people, right? And so I had to super conservative in producing results. And you're always living in fear that, you know, you find something you would retract. And as you are the only instrument, nobody will believe you after that. But so it's really a nice feeling to see all these other detectors come alive.
Yes, it certainly is. And there is a lot of action in this field. Well, Dune is in work for 2030 or 2032, CHEMET in the Mediterranean, U with expansion. So it's an interesting, and part of our goals in the program is precisely what is happening today, which was a nice surprise. David, it's a 10-year-old, which is doing the astronomy part with an astronomy club with the support of a great mom, by the way. But we are hopeful that in Guatemala, more kids get involved in these topics and get motivated to continue in STEAM-oriented career paths, particularly as usual, astronomy and physics. So unfortunately, and myself, I would personally love to have hours of our talk, but the time has come to an end. And we appreciate your time, Dr. Halzen. Again, we congratulate you on your recent honors, but we are certain that many more will come because it is an extraordinary work that motivates us all. So thank you again for being part of the Leon Lederman Seminar Series. And on this reboot of the Leon Lederman Seminar Series for the 2026, the next seminar will be for 11F with astronomer April Russell, former Astronomers Without Borders head. So we are having an exciting year, and hopefully we meet in some part of this year and this universe. Thank you again, Dr. Halzen.
A pleasure to talk to you.
It's always a pleasure. We always learn a lot from you.